So this lecture is about an important assumption that we often make on time series data. So remember, when we have time series data, we cannot in general assume that we have a random sample. We cannot assume that the sample points are independent of each other. In most cases, when we view time series data, there is a dependence between two observations uh, at different points in time, and we must allow this. Otherwise, if we still just assume that the data is a random sample, well, then the results will just be silly because we will know that that is not satisfied. So one of the important assumptions that we often make on time series data, which may or may not be reasonable, depending on the data, but in some cases certainly is reasonable, is the stationarity assumption. So let me point out from start that even if the data is stationary, we will allow dependence between two observations at different points in time. So we're not ruling that out by assuming stationarity. So here's the definition of stationarity. So we have a time series process, y1 through yt, for example, German interest rate from a certain point in time to another point in time. We say that this time series is stationary, and I have to add that there are a couple of different versions of the stationarity assumption, and the one that we are talking about is the sometimes called a weak stationarity, or stationarity in the weak sense or in the wide sense. For this process to be stationary in this sense, we have to satisfy three conditions. The first one is the following. The expected value of yt must be constant. It cannot depend on t. Now, it's not an easy thing to control if this assumption is satisfied, although it is often easy to see when it's definitely not satisfied. Here is an example of time series data that does satisfy the first condition of stationarity. It will actually turn out to satisfy all conditions. I know that because I have simulated this data and constructed it so it's stationary. This time series data, every observation has an expected value of 10 actually. Of course, that doesn't mean that every observation is 10, only that if I restarted time and did this over and over again, then every observation would be on average 10. In this data set, the random sample, the IID assumption, is really clearly violated. And the key thing to note that is the fact that we can observe cycles in the data. For example, over these observations, there is an increase and a decrease and then so on. If you have cycles in the data, that clearly tells you that the observation today depends on the value in the previous period. You get into a period where the observations are generally very high, like here, and into periods where the observations are generally low. Since I have simulated data, I can also simulate restarting time and observing a new time series by just doing the F9 button, and I get various data series which are all stationary. Expected value is always 10, even though there is a dependence. In this dataset, I have simulated it in such a way that it's actually not stationary. And the violation is the first assumption. The first part of the stationarity criteria is that the expected value of yt should be constant. That is not the case in this example. In this case, the expected value of yt increases over time. We can see that if we F9 it, in each case, in most of the cases, because it's stochastic, there is a very clear tendency for this to increase over time. Unfortunately, if I just observe one time series like this, I cannot just conclude conclusively that this is not stationary because there is an increase in expectations over time. Because I don't know what happens afterwards. It could very well be that the expected value is constant equal to 40 and that we're just in a period where this data is increasing, and perhaps after this time period is over it will come down again and go below 40. That is certainly a possibility. So to evaluate whether the first condition is satisfied or not, we also have to think a little bit about what time series data are we talking about. For example, if YT is, let's say, GDP, then it's completely unrealistic to believe that that should be stationary, because we would then have to assume that the expected value of GDP is constant over time, which would imply that there is, in general, no growth in the economy. We would have to claim that the recent increase in GDP that we have observed is just temporary and it will decrease again. For other variables, such as interest rates, it's not so unreasonable to believe that the expected value is constant. There is no tendency for interest rate to increase over time like there is for GDP. The second criteria for a time series to be stationary is that the variance is constant over time and that it doesn't depend on t. This first time series that we looked at, here this condition is satisfied. There is no increase or decrease in the variance over time. The variation in the data looks pretty much similar over time. So let's look at a case where this is violated. Here is an example of a time series which is not stationary because the variance increases over time. In this case, the first condition, that the expected value is constant, is actually satisfied. The expected value is 10, but you can see that as we move along, there is not much variation in the beginning, but as time goes on, the variation in the data gets bigger and bigger. So this is not a stationary time series. The third and the final condition of stationarity is the hardest one to grasp. It says that the covariance between yt and yt minus s depends only on s but not on t. To simplify this, first think of s as being equal to 1. Then it says the covariance of yt and yt minus 1. That's the covariance between the observation in this period and the period before, right before. Now it says that that doesn't have to be 0, first of all. It doesn't have to be 0 because we are not making the IID assumption, but it cannot depend on t. So the covariance between yt and yt minus 1 must be constant over time. So the covariance can't increase or decrease over time. Similarly, for s equal to 2, then you have the covariance between yt and yt minus 2. That is between two time periods, which are two observations, which are 2 time periods apart. Now that doesn't have to be equal to the covariance between 2 sample points that are 1 time period apart. And in general, the assumption is that this covariance will then be smaller. So the further 2 sample points are apart in time, the smaller will be the covariance. So the covariance may depend on s but not on t. Here is an example where the third assumption is violated. In this case, the covariance between 2 sample points is much larger in the beginning and it's much smaller towards the end. We can see that because there are much more clear cycles in the beginning of the data and pretty much no cycles at all towards the end of the data. So this is a case where the covariance between two sample points actually depends on t. It decreases with t, and that's not allowed for stationary data, so this is not stationary. Now, there is a way of conceptually understanding this concept of stationarity without dwelling on all these details in terms of the technical definitions. Here again, I am looking at the first time series dataset, the part that was actually stationary. And I have done what's called a window of this dataset. The dataset actually has 500 observations, and I'm just looking at this dataset through a small window where this window goes from 1 to about 113 or so. So let's just conceptualize thinking of this window as we move this window a little bit to the right. So we look at a different part of the time series. So we move this window over to the right like this, and so on, all the way until we get to the end. So here's the idea behind a stationary time series. The idea is that when we do this, look at the data through a window like this, it should look pretty much the same no matter where we put the window. If the data looks pretty much the same independent of where we position the window, then it's stationary. If I look at this data set through a window, then initially it looks pretty stationary, but we can see that as I move along, then suddenly something happens. It doesn't look at all the same through this window as it does through this window. So this is not stationary. So finally, let's look at a couple of results that are useful when dealing with stationary time series. We are not going to prove them in this lecture, just note them. The first one is the following. If I have two stationary time series processes, then if I multiply each observation of the first time series process, the yt, with the constant, so I get cy1 all the way to cyt, then it's still going to be stationary. For example, if the expected value of each yt is 10 and c is 2, then the expected value of each in the new time series cyt will be 2 times 10 and or 20, but still constant. Second, if I add two stationary time series together, the result will still be stationary. For example, if the y sequence is stationary with an expected value of 10 and the x sequence is stationary with an expected value of 5, then this new time series, which is the sum of the y and x, will be stationary with an expected value of 15.